All right, so on page 7, number 1 is 3. Number 1 is 3. Number 2 is 3. Number 3 is 2. Number 4 is 1. 5 is 2. 6 is 2. 7 is 2. 8 is 3. 9 is 3. 10 is 2. 11 is 2. 12 is 2. 13 is 2. And the last one is all done with ruler and protractor. So you're going to have to measure things out with me. So the first thing they wanted you to do on page 9 was to construct the sequence of the 2 displacement vectors. So when you do this, it should look like this, but we got to measure it all out because they gave you a scale. So let me show you how I'm going to measure this if this were your quiz. The first vector was 200 meters going north, so we need an arrow that's pointing up on your paper. It should be labeled 200 point meters. You didn't have to say north. In the scale they gave you, where 1 centimeter was 50 meters, when we measure it out from the tip of the arrowhead to its tail, we get 4.0 centimeters. We do need an arrowhead at that very tip, so that way it's exactly 200 point meters. Then you had to go east. East is directly 90 degrees to the right. So you need your protractor now to verify that you actually have a 90-degree angle at that point in the triangle, like that. So I can see that from here to here is exactly 90 degrees. That's the next thing to check. The next thing we want to do is check your 300-meter east vector is pointing to the right. So you have an arrowhead that points to the right. And when you measure its length from the tip of this vector all the way up to the tip of that one, you get 6.0 centimeters. Make sure that length is correct. Now the next step, step A2, said construct and label the vector that represents the resulting displacement from point P. So the displacement is this arrow in green that we're going to connect here to here. We should have an arrowhead that points up, and we should be labeling it D with the arrow over it, just like we did with the in-class questions. All right, now part B says, what is the magnitude of this resulting displacement? To determine the answer, because it's all ruler protractor, you just use a ruler to figure this out. So we're going to measure it, and when I measure it, I get 7.0 centimeters. So in this scale, I'd be saying it's about 350 meters. The correct answer is somewhere between 361, well, plus or minus 15 was the tolerance they gave you. So 346 meters up to 376 meters is what was allowed. And then in part C, it says, what's the angle from the north to here? So that's the angle I want. That is not the angle I showed you how to measure in class, but according to the directions, they want it from the north, which means we're going to take our protractor and we're going to place the north as our reference of 0. And we're going to measure over from here. And as you can see, that's giving me 56 degrees. You're given 2 degrees of leeway around that. So anything from 54 to 58 degrees would be allowed. All right. Any questions? Yes. No, they wanted you to do this with ruler and protractor. I'm sorry? Yeah. You should get the same thing, but I'm not grading the math on this. As soon as we tell you to start drawing it, you get all your answers by measuring. Okay, so what we do, measure the length of your displacement vector. Actually, I'm getting more than 7. I'm getting like 7.2. So 7.2 times 50 gives me about 360. And they said the accepted answer, New York State, this was a Regents question, said the answer was 361 meters, but they gave you 15 meters of leeway. So that means we would be taking anything between 346 and 376 meters if you've done it correctly. Okay. Yep.
Can you show again how you measure theta?
Yep. So they asked you to measure from the north. Well, north in this picture is up here. That's our reference line then. So we have to measure from here over. So we're going to put our origin at point P. And I'm going to line up my 0 with north. And then I'm going to measure the size of that opening this way, and that's how I'm getting the 56. You're welcome. Anything else?
So like when you use the ruler to calculate the displacement or like the equation, 8 minus
Yeah, what's your question?
does it matter?
Yeah, this one was measured. It was all drawn, so you should be measuring it.
When did you use the equation?
If you have a right triangle on a multiple choice question, like any of the other problems that were assigned. Anything else? Yeah, let's go over number 8. So number 8 asks you which vector represents the displacement of 3 meters west and 4 meters south. Hopefully you eliminated 1 and 2 right away because we went west and south, which means your resulting displacement is somewhere southwest. These are pointing somewhere northeast. So those are no good. Okay. So we went this way 3 meters and then we went down 4 meters. So that means the displacement is pointing down and left like that. Okay. Now, here's the way I would recommend you figure out 3 and 4. It's all visual. You do not have to calculate it. Draw in the right triangle where this is the hypotenuse with one side on the vertical, the other side on the horizontal. And as soon as you do that, you'll see that in number 3, the horizontal side is shorter than the vertical side, which means this has to be 3 meters and that's got to be 4 meters. On this one, number 4, the horizontal side is larger than the vertical side, which means that would be the 4 meters and this would be the 3 meters. Well, which one has it drawn correctly? Yeah. Therefore, that's got to be the correct choice. So it's visual. You didn't have to calculate anything. Anything else? Yep. Question number 3. This one here says that she's swimming directly across a stream, which is 15 meters wide. And when she gets to the other side of the stream, she's 15 meters downstream. That means she went this way 15, but ended up 15 meters that way. So what is the displacement? The displacement here is the hypotenuse of that right triangle. So you would solve that using Pythagorean theorem. Anything else? Yeah. Number 1 asks you for the magnitude of the total displacement of this school bus from the start to the end of the trip. The displacement is measured from the starting point to the ending point right there. That arrow I just drew is the displacement arrow. How long is it from here to here? Well, I see from here to here is 400, but then from here to here is another 400. So the displacement is therefore 800 meters, and it's pointing east or to the right. So the best choice is 3. Displacement is always measured from the start to the end. Draw an arrow between those 2 points. Start to end. Start to end, always. Anything else? Okay. Then what I'd like you to do is turn to page 9 in your packet. You've got some extra space on this page that you can use for scrap paper as you take today's quiz, which is in Google Classroom. So go ahead and open up Google Classroom, and you can go ahead and take the quiz for Unit 2A. You may need your ruler, your protractor, your calculator in the degree mode, and your pencil to work out these questions on the scrap paper, okay? Good luck.
do exist biology conduct in IT, but not as an exam. So how should I?
I would try turning it off and then rebooting it,
Yeah.
and it's still doing that. Okay, just take the quiz later today.
Okay, thank you.
But you're going to need a pass to IT because you're going to need it for lab 4.
Okay,
So I can't create a pass. So let me do that right now.
thank you. Should I go right now?
Wait till I get the pass going. No talking. Just waiting to make sure. Yeah, you're all set.
Thank you.
You're welcome. When you're done with the quiz, keep your Chromebook out because the next thing we're going to do, as you can see up on the screen, is finish lab 4, which is in Google Sheets. You can open up that lab on your Chromebook. Your quiz is turned in. Let's see, I'm still waiting on. All right, so folks, let's look at lab 4. Lab 4, which was this one here that we started last week. And let me just make this a little bigger. We're going to work on getting this lab finished and turned in. And if you follow along with me, if you've been following along, you should be able to get 10 out of 10 on this lab. Okay, because I'm going to do the entire thing with you. So let's look at where we left off last week. Remember that what we were doing last week, we started on the experiment tab, and we were able to mark out the positions of 6 different buggies out in the hallway along a 10-meter long meter stick or measuring tape. Remember doing that? Okay. These were the positions that your groups measured. What we're now going to do is create a position time graph that goes with this data table. And I'm going to tell you now, Google Sheets gets this all wrong. I don't know if it's the way that table is formatted or what, but we have to customize this thing. It takes like about 800 steps to get to the graph to look the way we want. So I really need you all to pay attention and follow along with me, because if you miss a step, the graph, you're going to have to delete it and start it all over. Okay? So could you please all put your cursor in cell A23 where it says time in seconds, so that's highlighted. Hold down your shift key, right arrow over, and you'll see it then selects your position and the car numbers. Keep your shift key depressed. Use your down arrow key and select all of the rest of the data. So that way up here in your name box, it says cells A2 colon G10. That's what it should say. A2 colon G10. All right. Everybody got that? Without that selected that way, it's not going to give you the right data in the graph, and you're going to have to delete and start over. All right. So now we're going to go up to the insert menu and say insert a chart. And I'm going to tell you, you'll see right now, boom, that is the graph it gives us. That is not what we want. It gives us the wrong type of graph. I don't know why Google Sheets wants to make this a bar graph, but it does. So let me show you how we fix this. Everybody have their chart editor window opened up? Okay. There are 2 options at the top. The left one says setup. The right one says customize. We're going to start in the setup section. Come down under chart type and change that. The type of graph we want is called a scatter plot, a scatter chart. You'll see there are 2 options. We want the one on the left. Select that. Now it's starting to look more like what we want, but there's still a lot of things missing that are normally there for us. Double check these other things on the setup tab on the chart editor. The data range should say A2 colon G10 right here. For x-axis, it should say time in seconds. And then for series, you should see car 1, car 2, car 3, car 4, car 5, and car 6, all labeled. If anything is not labeled, we have to delete and start over. Then double check, you should have use column A as labels checked off. Are we good so far? Okay, go to the Customize tab then. This is where we have to add a lot of things. The first thing we're going to add is under the submenu Chart and Axis Titles. We are missing a title on this graph. So select Chart Title. For title text, this is position versus time. This is a graph of position versus time, so go ahead and type that there. Now we are missing a label on both the X and Y axes. So select the down arrow, and now let's go to the horizontal axis title. We're going to tell Google Sheets what was on the x-axis of our graph, which should be time in seconds. Now select the down arrow again, go to the vertical axis title. Again, there's no label on the y-axis. This was position in centimeters. Position in centimeters. Okay, you can now collapse that submenu. The next thing we're going to do as I look at this graph is I want to double check that I have a clear 0, 0 on each axis. I do. If I didn't, I would have to add it. We're good. Do you all have a 0, 0? Okay. Now we're going to go to series. And what we're going to do is add a trend line for each set of data. We need it to say apply to all series. Come down, select trend line. And these all should be linear. So the type linear is correct. But we also want Google Sheets to display the equations for each of those lines it just drew. So under label, please say use equation. We are now done customizing. So you can close your chart editor. And this is what we should see. Let me make this a little smaller so it shows up on the entire screen. There we go. Your graph should look like mine. We should have all the same points. This thing on the right side of the graph is called a legend. It is a key. So it tells us that anything in this bright blue is for car 1. Anything in red is for car 2. Anything in yellow was for car 3. So that's a key so we can see all 6 cars on the same graph. It helps us identify patterns, which is part of what this lab is about. Does everybody have that? Okay. Before we move the graph down into the yellow space for graph, I'm going to keep it right there. I'm going to move this up. And you'll see that on the right side of our Google Sheet, I'm asking you for the equation for each car. We're going to use the Google Sheet equations for each line to help us write this. I'm going to do the first one with you. Then I'll freeze my screen and ask you to do the other 5. Okay? So let's look at the equation for car 1. Remember that it's a line, so it should take the general form of y equals mx plus b. And the Google Sheet doesn't tell us what y is. Doesn't put y equals. We have to look at our graph to figure out what is on the y-axis. So according to this graph, what's on the y-axis? What variable name? Position. So in this box for equation for car 1, we're going to start by typing position equals. That's our y equals. Now, M. What does M stand for? Slope. We're going to put this in parentheses. Now, the value doesn't have a sign in front of it. We need a sign. You're going to learn in about 3 minutes what the sign means in physics. What's the sign for the slope for car 1? Positive. So please put the positive sign. Then we follow by the number 12.1. Now we have to add the units of this slope. Remember that slope is always units of the y-axis over the units on the x-axis. So what do you think the slope is going to be measured in? Centimeter over second, cm/s. Close your parenthesis. Now we're going to change the letter x in the equation to the name of the variable on the x-axis, which is time. Plus, now we need our y-intercept, 0.929. And now we need a unit on that y-intercept. What unit am I going to put on that y-intercept? Thank you, Mariah. Centimeters, cm. Hit enter. And that's what you should have for your equation for car 1. Can you do the other 5? Do the same thing with the Google Sheet equations, and then we'll compare at the end that you have the right stuff. answer, sure. Seven. That is correct. That's actually should be fine. Should be fine. 6 and keep going down. Now, I think that's nice. Yeah, that's correct. Okay, go customize. Go to chart next titles. Chart titles should have typing position versus time. Now, click the down arrow. And now we're going to go both the X and Y. Nope, not yet. See that down arrow? Same horizontal axis title, type in time and seconds. Okay, now do the vertical axis title, choose position and centimeters. Good. All right, collapse the submenu. That's that for the series. You have a 0, 0, so that's good. We want to apply this to all of the lines. That's good. Run down, select the trend line, go down, change the label from none to use equation. There you go. No R squared. All right, now you can collapse this, and now you can write the equations taking the same form staff for all of those. Okay, I'll give everybody another minute to get those done, and then we'll check. Check that you have the correct equations for all of them. Make sure you're not missing anything that you need. The rest of this goes pretty quick. All right, so I'm not worried that we're spending a lot of time on it. I want to make sure you've all got it, so that way we can turn it in, get a 10 out of 10. That way you don't have to do lab corrections. Okay. Can we start checking them? Yeah? All right. Let me see if I can make my screen a little bigger. And then I'll unfreeze it. Yep, that's good. All right. So let's start with car 2. You should have typed position equals parenthesis positive 38.2 cm/s, close the parenthesis, time plus 16.7 cm. Everybody good with that one? That should match what you have here on the Google Sheet trend line. Number 3, you should have typed position equals parenthesis negative 35.6 cm/s times time plus 1006 cm. And that should match what Google Sheets gave you for the equation. Number 4, you should have typed position equals left parenthesis negative 37.4 cm/s, close the parenthesis, time plus 996 cm. Your proofing errors, right? Checking it. It should match what you have over here for car 4. Car 5, you should have typed position equals positive 36.4 cm/s, close the parenthesis, time plus 509 cm. If any of your numbers are different, you either mistyped it or you input a data point incorrectly in the original table, which means you got to now figure out where you have an incorrect value typed in. Equation for car 6, you should have typed position equals parenthesis 0 cm/s, close the parenthesis, time plus 500 cm. Everybody good? All right, let's take our break. When we come back, we're going to work on the analysis and conclusion tabs to finish this up. Brian, if you want to take the quiz now, you can.
I put the same twice.
Okay, let's see. I gotta move this down, get it out of the way. Whoops. So the last three should be 100. Okay, so you're missing up above 0, 25, 49, 75. So go up here, change that to 75. 100, 121, and 145. And that should change what you have here. Yep, okay. So you're just going to take it at home that night. So Mr. Walter will be here because I'm actually not going to be here Wednesday because I have testing that has to happen during the day. So you'll just follow the videos and what it says in Google Classroom. He won't check your homework because you're going to be marked absent. So you just watch the videos at home, get yourself caught up, and just do the stuff at home. Okay. That's actually a great question. So in case anyone's absent when I'm not here, beginning Wednesday of this week, if you're ever absent, everything is going to be posted in Google Classroom for the next couple of weeks. All your quizzes are going to be turned in that way. Every assignment that I need to grade will be there. The only thing that you're not turning in Google Classroom are your daily homeworks. Mr. Walter will be coming around the room just like I do to check your homework is done and making a note. But if you're not here, you're just going to take the quiz at home. You're going to watch the videos at home instead of being in class to watch them. And if the class, for whatever reason, doesn't get through the video, part of your homework will be to finish the videos for homework, right? Because I've got everything scheduled and one video goes into the next, which goes into the next. So if something isn't finished and they start the next video the next day, you're going to be missing a chunk of stuff. You understand what I mean? Because I'm not going to be here to monitor your progress with those videos. And I'm not asking Mr. Walter to do that either. He's just saying, here's the video for today. Let's watch it. And when it's done, what questions do you have that you saw in the video that you don't understand? Let me help you. That's what his job is here for. He's here to help you figure out what maybe you missed in the video. All right, so on this tab, before we go on, I now need you to take that graph and drag it down to where it says graph. You have this yellow box. Go ahead and do that. I'm going to make mine a little bit smaller, the screen, so I can place it. Now, if it doesn't fit, you know that you have these little blue dots around the graph that allow you to resize it. So go ahead and resize it to get it to fit in that yellow box that's there. That way it's not covering up your data tables. It's not covering up your equations. Go ahead and resize that. Now remember, if you're going to sleep through class, I'm happy to give you a 0 for today. And make a note in Aspen so your folks see it that you have a 0 for not participating. You are not able to engage in the class if your head is down and you're sleeping. All right, any questions on this? All right, let's then move on to the analysis tab. And I'm going to make my screen bigger again so we can see. We now want to answer questions here about the graphs. And it's telling us which set of questions get answered with which graph. So let's start with question 1. Questions 1 through 5 are based on the graphs that we have for car 1 and 2. So if I go back to the experiment tab and I look at these graphs, car 1 is this bright blue one here at the bottom, and car 2 is this red one. All right, you've got them. We're going to be going back and forth to help us answer these 5 questions. So the first thing, are our data points falling in a somewhat straight line? Do these look like they're making a pretty straight line? Yes. Okay, so let's answer that in a complete sentence. Yes, the data points create straight lines. Okay, now question 2. What physical quantity is represented by the slope of the line on a position time graph? So let's look at these graphs for a minute for car 1 and car 2. Who had car 1? Do you remember which group had car 1? Your group had car 1. And who had car 2? They started at the same position, right? But there was something very different about those 2 cars as they went down the hallway. Anybody remember? Those two groups probably remember when you were watching them on the floor, how they were moving. There was something different about them. One was faster. Do you remember which one was faster? Car 2 was faster. Now take a look at these 2 graphs. They both start at the same place here, but do you see how car 2's graph looks like that, where car 1 only looks like that? What's different about this line that indicates it would be going faster? It's slope. It's steeper, okay? So the slope is giving us something called the velocity. So the velocity, which means the speed and the direction of motion, are indicated by the slope of the line. And you plug into that yellow drop behind you. You're welcome. Okay, so this is a physics term that's going to be formalized in our notes in a few minutes. Velocity. Velocity refers to the speed, how fast it's moving, and the direction it's moving in. So how do the slopes for those 2 cars compare? And what does that mean? So let's look at the slopes. Car 1's slope was 12.1 centimeters per second, positive, and car 2 was positive 38.2 centimeters per second. So how does this compare to that? So the slope is, look at the number. The number is bigger. Okay, so let's go ahead and answer that question. The slope of car number 2 is larger than the slope of car number 1. Now, before we continue, anytime we say the word compare in a question, I don't know why it's frozen. We just got to wait. It's not replicating. The question says compare, right? It says compare. Compare wants to know what's the same and what's different. So we just said that the slope of car number 2 is larger. That's a difference. What's the same about them? That's not a slope. That's a y-intercept. Okay. Mia? There you go. Okay. So, and I don't know what to do here to get it to replicate. I'll try doing this again. Let me see if I change my projection status. There we go. Now it's starting to wake up. Is it there? No, it's still not there yet. And I don't know why. All right, well, listen. We just said that the slope of car number 2 is larger than the slope of car 1. But what did we say is the same? Yeah, what did we say it's the same? Okay, so we're going to say the slope of car number 2 is larger than the slope of car number 1, and both slopes are positive. Okay, so what does this mean? What does this mean? So because car 2's slope is larger, what does that mean? It means it's traveling faster. And since they're both positive, what does that mean? Nope, not speed. What did we say the velocity is? There we go. I don't know why it's taking so long to replicate here. The velocity, which is the speed and the direction. If they're both positive, what's a positive? It's a direction. So if they're both positive, what does that mean? What do we usually mean is positive? This was, okay, so we're looking at the hallway, right? Where was 0 in the hallway? Down here. Both of those cars were going which way? That way, to the right. I'm gonna make sure I'm the one who's, I'm going to try disconnecting and then reconnecting and see if it will go. So something's up with that Bluetooth connection, obviously. And there's nothing I can do about that. Wouldn't matter what I was working in, it would be messing up. But right now it looks like that. Okay, here's what I'm going to do. Shut it off. And then I'll turn it back on and see if it works better. Okay, in the meantime, we can continue typing. So we said that the slope of car number 2 is larger than the slope of car number 1, and both slopes are positive. So this means they are both moving to the right, but car number 2 is moving faster. There we go. Just updated. Give it a second here to. There we go. So that was my answer there for that question number 3. Okay, can we go down to question 4 then? Are the velocities for car 1 and car 2 constant or not? And how do we know? Remember how we get velocity. Velocity is the slope of our line. So look at those two graphs, car 1 and car 2. Are the slopes the same everywhere? Is the slope of car 1 the same from 0 to 6 seconds compared to 6 to 12 seconds? How about car 2, 0 to 6, 6 to 12? Are the slopes the same? Yeah. Slope is the steepness. The slope here is the same as it is here and here and here. That's the neat feature about a line. They have constant slopes. So are the velocities constant? Yes? How do we know? Because they're lines, and lines have constant slope. So both graphs are lines, and lines have constant slope. All right, so number 5 is asking you, if you were to look at a position time graph for an object that was moving with a constant velocity, how would you recognize that it had a constant velocity? What would you expect to see? Be more specific. What kind of lines are those two graphs? Diagonal lines. Okay. So how would we recognize a position time graph for an object traveling at a constant velocity? The graphs would be diagonal lines if the object is moving with a constant velocity. Okay? So far, so good? All right, let's then look at graphs 3 and 4. So let me go back to the experiment tab. You can do that as well. Look at your graph for car 3, which is my yellow one, and car 4. The yellow and the green right here. Yellow and green. That's car 3 and car 4. We're going to compare that to what we just saw for car 1 and car 2. So number 6, what do you notice about the shape of these graphs? Are they similar to the graphs for car 1 and car 2, or are they different? Shape. What is the shape of the graph for car 3 and car 4? Is that the same or different than car 3 or 4? It's the same. Okay. So the graphs for car number 3 and car number 4 are also diagonal lines. This is the same as car number 1 and car number 2. Undo what I just did. There we go. All right, number 7, how do the slopes of the graphs for 3 and 4 compare to the slopes for car 1 and car 2? So let's look at their slopes. The slope of car 3 is right here. There's the slope of car 4. How does that compare to car 1 and car 2? There's a big difference between them, right? What is the big difference? They're negative. What does that mean? Which way? To the left. We said 1 and 2 were going right. So 3 and 4, negative is left. All right. So let's answer that. So the slopes for car number 3 and car number 4 are negative. This means they were moving to the left, whereas car number 1 and car number 2 were moving to the right. And are the velocities for car 3 and 4 constant? How do you know? What are we going to look for if their velocity is constant? Take a look at number, what question is that? 5. Is the velocity constant? Remember, we said, how would we recognize a graph if the velocity is constant? What would we see? A diagonal line. Do we have diagonal lines for 3 and 4? So is the velocity constant? Yes. Okay. So yes, the velocities are constant because these graphs are diagonal lines. Make sure you hit enter after you type your answer so Google Sheets saves it. And if you move out of the cell where you typed your answer, it should stay there. Okay, that's another way to make sure it saves it. I know in some of the other labs that were Google Sheets, you may have typed an answer, but you didn't move out of the cell, so it doesn't save it. When you turn it in, I'm telling you it was blank. You didn't answer the question and you lose points. So you always want to make sure after you type in a Google Sheet, you move out of the cell so it saves it. That's different than Google Docs. Nothing I can do about that. Okay. Any questions on the analysis tab? All right, let's use that information to fill in the blanks for these 7 statements on the conclusions tab. Please don't change the font or the color. We're going to type on all those little red lines. So I should be able to just see your answer in red to fill in the blank. Let's do this together. Number 1, if you have a linear position versus time graph, that tells you the object is moving with a what? Thank you, Nikki. That's correct. With a constant velocity. So let's put our cursor in the middle of that red line and type constant velocity. All right. Statement number 2. What does the slope of a linear position time graph tell us about the object? The slope is the velocity. And what do we mean by a velocity? The speed and direction of motion. That's both of those. It's going to tell you how fast you're moving and in what direction you're moving. That's what we call the velocity. Number 4, we didn't talk about this, but let's see if we can figure that out. The y-intercept on a position time graph is going to tell us what about the object? So let's look at the graphs. These y-intercepts, what were they telling us? Sorry? The starting point. We call the starting point the initial position. So the y-intercept tells us the initial position, which we call the starting point of the object. The physics term is initial position, where you started from. All right, the faster an object is moving, the blank the position time graph will be. The faster it's going, if I just look at my graph, how can I tell that car 2 is going faster than car 1? It's steeper, so there we go. So the faster an object's moving, the steeper the object's position time graph will be. Which means that the slower you're going, the... What's opposite of steeper? What is it, Eric? Flatter or shallower? The term we usually say is shallower. If you're traveling to the right, you're going to have a what slope? What type of slope? Positive, that's right, a positive slope. And if you're traveling to the left, you're going to have a negative slope. Again, make sure you hit enter after you type it, move out of the cell so you can see I'm moving all around and it's keeping my data that I typed in. Once you've done that, you can submit the lab. That is the lab. It's done. Turn in lab 4. And then you can put your Chromebook away. What you'll need for the rest of our class today is your notebook. Go ahead and get out your notebook. And we're now going to move into section 2B. Or not 2B. That is the question. Can you name that play that comes from? We'll get you your ELA lesson right now. To be or not to be? Anybody know what that's from? There's a character, very famous character said that. Shakespeare. Hamlet. Have you guys ever read Hamlet in English class? Maybe that's this year. I know you do Shakespeare at some point. You have to read a Shakespearean thing. Usually it's either Hamlet or Macbeth. I think Hamlet is the better one. But anyway, that's a very famous quote from Shakespeare. Hamlet says, "To be or not to be." So since we're in Unit 2B, I just throw that in there. So anyway, now you don't have to go to ELA today. Yes, you do. Don't tell your ELA teacher I said that. But you can say, we learned about Hamlet. To be or not to be? That is the question. They'll appreciate that. Any of you have Mr. Wayne? Yep, you can tell him. He knows. It'll be like, oh, you're in physics. Miss Famoso, right? Because I do that kind of stuff all the time. All right, let's get started with Unit 2B. Unit 2B is about the topic of position versus time graphs, which we just made in the lab. And this is why we're following it up. Now that we've seen it in the lab, we should be able to understand these notes a little bit better. We have some experience with objects where we created a position time graph. Remember that the term position refers to where an object is located. And in this unit, we're going to say on the x-axis. Okay, we're going to do this on the x-axis only in Unit 2, which means we're going to be dealing with things moving left and right. So let's make an x-axis here. This is the positive x direction. Let's say our origin is right here. These are all going to be in meters. So that's our origin. I'd have +1, +2, +3, +4, -1, -2, -3, -4. Let's say I have an object located right there at time 0. Do you see where I just put a dot? At +3 meters. I would then say that the position there is +3 meters. Remember what that means. 3 meters to the right of the origin. Without the positive sign, I don't know if I'm right or left of the origin. We need that positive sign on it to tell us in what side of the origin we're on. If I just said 3 meters, I would either be here or here. You understand? I wouldn't know which position we were at. Now, since we're dealing with the x-axis, we're going to use a symbol of x for position only. Only the x coordinate is what we're going to work with. Now, to create our position time graph, I want you to imagine that we are going to rotate this by 90 degrees. And that will create our vertical axis on the graph with our position on the y-axis in meters. Here's my horizontal axis with the time in seconds. So the title of this graph would be position versus time. And that is my origin right there. This position is right here. I've rotated it. I'm flipping it 90 degrees, which means here's +1, +2, +3, +4, -1, -2, -3, -4. This position that I just marked, +3 meters at time 0. Well, let me put my times on here. 1, 2, 3, 4, 5, 6, maybe up to 7 seconds. I would mark this position of +3 meters when I start my stopwatch by putting a point right there. That's my y-intercept. My position at time 0 seconds is my y-intercept of whatever graph I end up creating. So we can see how this looks like that. I just took this and flipped it this way. Everybody with me so far? Okay. Since position is on the y-axis of my graph, we would say that is the dependent variable. And since time is on the horizontal axis of the graph, we would say that is the independent variable. Okay, let's now talk about the term velocity. What is a velocity? Some physics vocabulary here. We just kind of define that in the lab. Remember, when we deal with a velocity, we're talking about how fast an object is moving and when we say how fast an object is moving, before I do the and, that's referring to the object's speed and the direction the object is moving. So there's two pieces. How fast with a direction. Since we include a direction, do you remember what kind of measurement we would classify this as because it has a direction? A vector. This is called a vector measurement because it includes two things. It includes a magnitude, which is going to answer the question, how fast? So this is your size or amount. The magnitude of a velocity is what we would call your speed. It's telling us how fast you're traveling. And the other piece it needs is the direction that you're moving in. That's what makes it a vector, the direction piece of it. So the symbol that we're going to use for velocity is a V. V for velocity, but because it has a direction, we're going to put that little arrow over the top of it to remind us it is a vector. The units that we're going to measure this in the metric system are meters per second, which we abbreviate as m/s. Now, here in the United States, where we use the English customary units, we would say miles per hour. That's a speed. Okay. Let's now define speed. Can I go on from this? Okay. So what is speed? Speed answers the question, how fast an object is moving. How fast is the object moving? Since there is no direction on this, do you remember what kind of measurement we would call it? Scalar, that's right. This is a scalar measurement, which means it has a magnitude only. There is no direction on these measurements. The symbol that we're going to use for speed is also a V, but because it's a scalar, we do not put the arrow over the top. And the units that we're going to measure this in, again, in the metric system, are meters per second, m/s. Okay, so let's play a little game. I'm going to give you 4 measurements, and I want you to tell me what they are measurements of. All right, so 4 measurements. 40 meters per second north, 40 meters per second, 40 meters east, and 40 meters. Can you identify what those are measurements of? Anybody tell me what any of those 4 are? This is a velocity, V with the arrow over the top. That is correct. I've got a speed and a direction. So that is velocity. Shane? 4 is a distance, D by itself. Very good. How about 2 and 3? Mohammed? I'm sorry, 3 is a displacement. That is correct. What's 2? That's just a speed. Very good. That's a speed. Understand how you can tell? You're looking at the units first to narrow it down. And then if it has a direction, it's got to be the vector piece of that. Okay? All right. So how do you get velocity from a graph of position versus time? Now, position is the letter X, so sometimes you'll see the graph titled just X versus T. Position versus time. So how do you get a velocity from the graph? We just did this in the lab. Do you remember what you're looking for on the graph to give you the velocity? The slope, that's right. So the slope is going to equal the velocity, which is going to tell us how fast you're moving, your speed, and the direction you're moving in. So let's try to summarize some patterns then. If you have a positive slope, what does that mean? Remember from the lab, what does that mean if your slope was positive? Logan? Yeah, that means you're moving to the right. What about if you had a negative slope? Nathan, what would that mean? That's correct. That means you're moving to the left. What if you had a 0 value for the slope? You had a 0 value for the slope. What would that mean? What do you think, Dan? Yeah, that means you're not moving at all. You would not be moving. If you had a large slope, meaning your graph was steep, what would that mean? That's right. Very good, Mariah. That means you're moving fast. How about if you had a small slope? In other words, your graph was pretty shallow. What would that mean? What? Yeah, that means you're moving slow. One last thing. What does the y-intercept tell you? It's on a position time graph, so that would be the initial what? Position, that's right, because it's the y-coordinate, which is a position, the initial position, which is your starting point. Okay, these are patterns. Let's now make a graph, sketch a graph of position versus time. So here is time in seconds. Here is the position in meters. I don't need any numbers on it other to know that's 0, 0. I'm going to draw 5 lines, and I want you to label them with me, okay? And then what we're going to do is try to define or describe the motion that each of these lines has. Let's call that line 1, line 2, line 3, line 4, and line 5. Okay, we're going to try to describe the motion of each of those based upon the patterns we just saw. So let's start with line 1. Can you tell me what the object that created line 1 is doing? It's not moving. Okay, line 2. Can you tell me something about how object 2 was moving? It's moving slow because it's a pretty shallow line. Can you tell me what direction it's moving in? It's moving to the right. How do you know that? Yes. So this is, I would say that this is moving to the right. With a slow, constant velocity. How about line 3? In comparison to 2, how is 3 moving? Bryce? That's right. So this one is also moving to the right because it still has a positive slope with a fast, constant velocity. All right, how about 4? What is 4 doing? It's going left. Is there anything else here going left? 5. Which one's going faster? 5. How do you know? It's steeper. So here's what we're going to do. 4, we're going to say is moving to the left. Hold on. With a slow, constant velocity. And 5 would be moving to the left with a fast, constant velocity. Okay, folks, your homework tonight is to study. Study and work on those test corrections. If you have test corrections, they go in that blue turn-in bin. Please push your chairs in, and I'll see you tomorrow. Thank you. See you tomorrow. Take care.